Stop your whining. It's the first thing on the recording, by the way. Stop your whining. All right, so this is where we left off last time, and we were talking about like patterns that you see in resonance structures, right? And just to remind you, electron arrows always start on electrons, lone pairs, 4 pi bonds, right? In a couple of these patterns, you'll have more than one arrow, but most of the time it's just one arrow. Right? So we have allylic lone pairs where you have to push this pair as into the bond space between the oxygen and the carbon, and then you should have a second pair of electrons, even though this arrow isn't starting from what we think of as the pi bond when we draw, right? We think of that as the pi bond. It's coming from this electron space, and it goes to this atom. So let me ask you a quick question, just reviewing. Why did I have to push a second arrow? Yeah, it breaks the octet rule, so you just have to be wary of things like that. And that's one of the things you don't want to do. Most of the atoms that we deal with, they're second period elements, right? Carbon, nitrogen, oxygen, fluorine, and they never go above the octet. Anybody remember why they don't go above the octet? They can only make 4 bonds. Why can they only make 4 bonds? Yeah, because they only have S and P orbitals. Remember, 1s, and then there's 2s and 2p, and then there's 3s, 3p, and 3d. And it was 3d where you could expand the octet. So you can, if you have a situation like this where there is already an octet missing, right? So just real quickly, on this carbon that's here, you know the octet is missing because of the charge. Ooh, that's a giant fat pen. Hang on, let me think I was goofing around. You have hydrogens here. Okay. So it's missing its octet. You can move that electron arrow. You know, over here, you're going to be losing the octet. And what's the charge going to be here after the electrons move? Positive. Because it lost the electrons, right? You can also take a pair of electrons next to a positive charge as long as there's an orbital available to create a pi bond. You can also move electrons towards a positive charge. You can also violate the octet rule. This is the only one that really creates a new violation of the octet rule by moving the electron pair towards a more electronegative atom. And then we also have, if it's a closed or cyclic structure with alternating pi bonds, you move all the electrons at the same time. Does it matter which way it goes? No, go either way. Okay, good. So that's just kind of a review. So now what we want to do is we want to talk about stability of contributors and what makes contributors more stable, as well as how does that influence the appearance of the resonance hybrid. They insist on sticking with this analogy. Let's say if we made a fruit that was 65% peach, 34% plum, and 1% kiwi, what would that look like? Answer?
What are the kiwi seeds?
Maybe. It would look mostly like a peach, right? Maybe it'll have short hair instead of long. Can you imagine if peaches had long hair? How gross that would be. Like, nobody would eat them. Be like, oh, I'm going to eat a peach. Oh, right? Sorry. So a lot of molecules have multiple resonance contributors, and they're not all the same. And so what you have to be able to do is recognize which contributors are the most important, okay? Because that'll tell you like where the charge most likely resides on the molecule. Okay, so a couple of things that we use to assess stability. It says formal charge generally decreases stability. So that sentence isn't quite complete. It's true that formal charge decreases stability, but if you're comparing, and that's the purpose that we have, right? If you have more formal charge than less formal charge, more formal charge is less stable. So it's by degrees. other things is you have to look at electronegativities. If you have a very electronegative atom, it generally doesn't like to have positive charges. Oxygen gets put in that situation a lot. And the other thing that could be said is, and it could be said two ways, complete octets increase stability, incomplete octets decrease stability. So I'm going to say all that, and then here's the other thing I will say. A structure is more stable if it has more stable contributors. The more stable contributors that you can draw, so what we're going to be doing is we're going to be drawing a molecule, we're going to draw all of its resonance structures, and then we're going to try to make an assessment. Does that make it more stable or less stable? And the more stable contributors something has, the more stable the molecule will be or the ion will be. Okay, so we're going to draw 3 resonant contributors for acetic acid. These are not all good. I would not draw them this way, but just to get the point across, what we're going to do is draw the 3 for this one. Let's do this real quick. I got to zoom into the right place. So the skeleton doesn't change. So I can draw the skeleton right away, and basically I'll be moving electrons around. Okay. So you know on the oxygen, how many lone pairs am I missing on this top oxygen? 2. What? And on this oxygen, I'm missing. It's a little trickier, but it's bonded to the H. It's still missing 2. So, using the patterns that we learned before, I have a more electronegative atom here and a less electronegative atom here. So I could do that. And so what that would do is create an oxygen with 3 lone pairs. And what else? It'll be it'll be negatively charged, and next to it's the carbocation, right? So a positive charge down here and a negative charge up here. And I started writing in red last week because we thought maybe it was easier to see. Is that okay? Yeah, okay. Ultimately, what would make this better to see is a better projector. Yes. I'm never sure until I'm done. But I've been really happy so far. It's been working really well. So this one will get like right after class. I'll finish it up and post it, and it should be up on my YouTube channel. Did I tell you how to search for that? It's Dr. K's Chemistry. And if you can't find that, you can find Mrs. K's Chemistry, and she's linked to me somehow. I'm not sure. Could be my wife. She started it. Actually, I guess I made a lot of videos before that, but they're pretty second rate, involving bad actors. All right, so that would have just been me. It would just me. Yeah. So okay, let's see. So the next contributor. Oops, come on, draw a pen. Again, I draw the skeleton. I still have that negative charge there. Like this. Okay. Oh, actually, I need to fix something real quick. I don't need that. Okay. Now, on this middle structure, what can I do? I can take this pair of electrons and move it towards positive charge, because that's one of those patterns, right? So then I'll end up with a bond like that, and it'll go like that. What's missing?
Probably a charge on the oxygen being positive.
Yeah, charge on the oxygen being positive, right?
On the homework, you wanted all 3 of them chalked out that way, didn't you? You didn't want just the last one showing the best distribution of
Yes,
charge.
you want to see all of them.
One.
Yeah. Like that one with the really long chain.
Yeah, with the 6 different ones.
Yeah,
going on.
yeah. You draw them all. when you get good at it, really, the purpose of doing it is to try to spot where charges are. It's relative stability. You can see where the partial charges are just by moving the bonds in your head, right, on the homework. Okay, let's see. Okay, so let's look at the stability of these contributors. There's 3 of them. And remember, the original structure is one of the resonance contributors. People forget that, so there's 3. What say ye? Let's take the middle one. Good or bad?
Not good.
Bad.
Yeah, bad.
Yeah, I'll just call it bad. Not good, bad. Well, not good could be like, well, it's all right, because this one's, well, anyways. Yeah, so not good or bad because it has a positive charge and a negative charge, and it violates the octet rule. Okay? So I know that's like a horrible structure, a horrible contributor. What about this one? Bad? But is it as bad as this one?
No.
No. So this one's actually better. Why is this one better?
Spread out charge and octet on that.
Even though it has positive and negative charge, and a positive charge in the oxygen is bad, it satisfies the octet for the carbon. And that's like a big deal. Like if you don't have an octet of electrons, you're usually a pissed off atom and you're looking for trouble. Okay? Sorry, it's Monday. It's been a long weekend. All right, so if you were to try to draw the resonance contributor for this, go ahead. Oh, this positive charge on this carbon means there's only 3 things attached to it, only has 6 electrons. And you kind of know that coming from here because you pulled the electrons away from the central atom. It was happy here, right? That's an octet. So if I remove the electrons in a resonance structure and put them up here, you know that it violates the octet rule.
So just that step in between violates it.
Yeah, yeah. But that is one of the patterns. Like they say, well, what we had like in the previous, right, over here, we had these 5 patterns of resonance. One of the patterns was, oh, you could take a pair of electrons and move it this way as long as this atom is more electronegative than that atom. But the problem with doing that, and the reason that's unstable, is it violates the octet rule. Okay, so we're back here. So if I'm drawing the resonance hybrid for something like this, I would probably, again, you draw the skeleton, put an OH here and an O here, and draw a dashed line where the double bond moves around. And at the top, you have a partial negative, and at the bottom, you have a partial positive. And you ignore that structure in the middle with the positive charge here because of its relative stability, it's pretty low. So let's do the same thing for acetate ion. Again, there's 3 contributors. I'm going to just draw them out fairly quickly. But they're following the same pattern as we had before. If it helps you, you can draw those H's out like that. Makes it easier to see the octets. And then the other one, oops, sorry. Didn't mean to draw the H on this one, though, did I? Let me do this. On the last one, you can draw the H's out. This one, you don't want to. Again, relatively unhappy contributor, right? Lots of charge. Violates the octet rule. And then the last one, and then I'll let you guys fill the arrows in. Looks like that. You guys following what I did with the arrows?
Just a question about the double bond in the middle one.
Yeah. Where is it?
Yeah.
Oh, yeah, so from here, the only thing I can do is to take this pair and move it up to here. So the first arrow, it's good. You have to think through these things. You move it up to here like that. And that's what gives you the positive charge here. You already had a negative charge here, and then here I filled in all the electrons that you should have. Right? And then from there, this pair of electrons, any of the pairs of electrons, can contribute to here, and that produces this final structure. And what you'll notice is the end structures are essentially the same. So we would say those contributors are equivalent. You have the same charges, same bonding. Maybe it's rearranged a little bit, but these are equivalent contributors. And like I said before, the more equivalent contributors you have, all right, the more stable the ion will be, or the more stable the structure will be. Okay. So the resonant hybrid for this one's relatively easy to do then. You put oxygens at the ends, dashed lines in between, and then what? Partial, negative, and partial negative. Okay. Again, this middle contributor, you could just ignore it. And in fact, when you think about it, there's another another resonance pattern that we talked about, the allylic lone pair. Yeah, that's the ultimate result of what we're doing with the allylic lone pair. We're recognizing that that middle structure is no good, so we always push two pairs of electrons at the same time. Okay.
If we recognize that we're going to need two arrows, can we just do it one step? Or
Oh yeah, I was just showing you why we did two arrows. But now it makes sense, right? It's like, oh, because before you're like, well, why do I have two arrows for this one? I don't have two arrows for these other ones. Well, the reason is because an intermediate contributor is so unstable that it's not really worth considering. Now, here's the problem. When you're first starting out and you're drawing resonance structures, you will draw a lot of bad resonance structures, and it's only after you look at it for a while you go, oh, why did I draw that one? And you'll just cross it out and you'll replace it with two arrows. Okay. Well, let's look at this one. Okay, first of all, let's evaluate this first structure. Okay. I don't know if I can fit them all in here at all. We'll see. Okay, nitrogen's actually got a positive charge, but he's happy because he has an octet. Okay, oxygen has a negative charge, but he's happy he has an octet. So basically, everybody's happy here, except for maybe a little bit of the nitrogen because of its positive charge. But that's really okay. So the first resonance structure can be an allylic lone pair. Yeah, you can do something like this. Because the structure you get in between will be just awful. If you choose to go in steps again, you're going to end up with something that looks like this. That's the intermediate that we kind of drew in the last examples, right? Where we just move the double bond but don't satisfy the octet by bringing in a pair of electrons. Okay, so the first resonance contributor could be something like this. It's so tricky drawing sometimes. You have to figure out, well, where are all the spaces that I'm going to put all this junk? There's one more.
Did you do the electronegative one with the double bond oxygen? Going to the double bond break? Oh, that's just the opposite.
So these guys are equivalent. I don't know if you can see that.
Yes.
All right, those are equivalent. The other one,
The double bonded nitrogen at the bottom.
like that. But if I do that, that violates the octet, so then the nitrogen has to kick a pair of electrons back. Again, this is not strictly one of the patterns we saw before. Are you guys familiar with drawing lines like that instead of electron dots?
Yeah.
It's much easier to see, much easier to draw. Okay. So we'll just move to that. That's negative. Now, something's missing. Positive charge on that. All right. Well, what do you think? So I got the ones I thought were really horrible are the ones we skipped by doing allylic lone pairs or pushing 2 pairs of electrons at a time. These 2 are equivalent contributors. What about this guy in comparison to them? Why is it good or bad? Answer that question. Bad. It's bad. So, but then the question is why? Too many formal charges, and now, what about this atom that's down here? Violates the octet rule, right? So a lot of things going haywire with this, but violates the octet rule. So I'll say non or no octet.
How do you know that there's not 3 hydrogens bonded to that?
Because when we started over here, there were 2 hydrogens here, and then, yeah.
I would have missed that one.
Yes, well, this is why we practice, so you'll get it. It becomes second nature after a while. You just have to do a lot of it. You can't just say, oh, on the test I'll remember, because you won't.
I'm confused as to when a resonance structure is done and complete, we can continue and then use that for the transformation of the next resonance structure?
As long as you can keep moving electrons and get different structures, you keep going.
And so
generally, the structures that you're given, you can follow some like reasonable pattern and go from one end to the other. But sometimes, like this one, we did one thing and then all of a sudden we switched up and we moved that pi bond off the carbon-carbon double bond. Yeah, you just have to recognize that that can be done. Now, the good news is, right,
only one complete.
this one's not stable. And so as a result, it's not a significant contributor. So if I was going to do the hybrid for something like that, which unfortunately I didn't leave myself much space for, but I'll do it up here in the gray space. Oops. Again, you just draw the skeleton. And then put partial positives and partial negatives. Whoa, I don't know what I just did, but I just undid everything. All right. No, I just somehow managed to erase everything.
Okay. Isn't there an undo button?
Oh, silly child. Is there an undo button? Of course there's an undo button. I don't know where it is. Oh, sorry. So let's just redraw it from scratch like this. Like that. Oh, actually, that middle one, because of the way I've done it, is just positive. Because that positive charge actually never moves from the nitrogen, so you could just make it a positive charge.
I thought I read in the book that, I don't know if it's just for the beginning of my understanding, but I thought violating the octet rule was only if you go over, not under.
Violating the octet rule is bad. You can't go over, because that's really bad. How's that?
So it is not having 4 groups, that's also
Yeah,
violating.
yeah. Not having 4 electron pairs of some sorts, either in pi bonds or single bonds or lone pairs, or triple bond and something else, right? That's bad. Like, so it's like, let's see, how do I put this? Okay. if you're put the analogy onto like driving, right? Okay, violating the octet rule by not having an octet is like a warning, right? And then all of a sudden they say, oh, but you have more than an octet, you're going to jail. Right? It's like you can't, it's illegal. It's like not allowed. Yeah. So degrees of badness, right? In the bad sense, not the good sense. Because like Clint Eastwood has certain degrees of badness about him. But that's a good badness, not a bad badness, right? Even though he's the old man. All right. So octet rule is usually a bigger factor than formal charge when assessing stability. Okay. So if you were to draw the resonance contributor for the structure on the left, right? Remember, pair of electrons to positive charge. That's one of our patterns. So like those patterns, you just got to do them over and over and over again. I can move this pair into here.
Pair of electrons to a positive charge?
Yeah, that's one of those patterns, pair of electrons.
One of those allelic things.
Yeah, it's like the fourth one in the patterns of there's 5. Yeah, you got to just practice them so you can see them. Because they don't always look the same. Like sometimes there's a nitrogen there, sometimes there's a carbon there. There's different atoms, and you can't be so restricted in your thinking that it's just a pair of electrons to an atom that has a positive charge. Okay. All right, so again, it's degrees of badness or degrees of goodness. It depends on, optimist or pessimist. Right now I'm being pessimistic. So compare those two. Based on that first sentence, which one's more stable? The one on the right. Generally, because right here, all right, no octet. Oh, I know. I'll do this. I'll make up my own symbol. There. That's almost longer than writing no octet. No 8. It doesn't have 8. Okay. And this has positive charge. But they both had formal charge to start with. So clearly this one's going to be better because it doesn't violate the octet rule anymore. What about here? Which way would, if you're going to draw a resonance structure here, which way would you move the electrons? Wait. What was that? Pi bond on the nitrogen? Or lone pair? I heard lone pair and I heard pi bond.
I said lone pair, but it's not what I meant to say. I meant the pi bond onto the nitrogen.
Yeah. Again, why is that? It's one of those patterns that they show. You have 2 atoms that are bonded together with a pi bond. The nitrogen's more electronegative, so the electrons move that way. So then what you end up with, ran out of space. Again, which one of those two do you think is more stable? What's that? On the left, because we're looking at charge versus octet rule, right? And so this one has doesn't have the 8. Gosh, that's easier just doing that. Oh, did I skip a slide? No, I didn't. Okay, so we got to talk about localized and delocalized electrons. Localized electrons are not in resonance. So the most common localized electrons that we see in resonance structures are the ones that never move. Yeah, sigma bonds, right? Oops. So sigma bonds for sure. Now, delocalized electrons are in resonance. What kind of electrons are those generally then? They're either pi bonds or lone pairs, right? Okay, so to be delocalized, electrons have to exist in an unhybridized p orbital. That's usually the pi bond, right? And it has to be able to overlap with a p orbital at a neighboring atom, which means, right, the neighboring atom can't be sp3. It has to be either sp, because that has 2 unhybridized, or it's sp2, right, because there's 1 unhybridized. And if you forget that rule, right, you just draw it on your fingers. You go SP, P, and P, and you say, well, if it's SP2, oops, sorry, SP2, sorry, that was SP. If it's SP2, then there's 1 unhybridized. If you have any pinkies folded down, this is the unhybridized orbital. Right? So you know that in SP3, when there's 4 groups, there's no unhybridized orbitals because you don't have 6 fingers. Okay. Well, I don't know, I just made that part up. Okay, so that's what this part means. It has to be SP or SP2. Now, I'll also make this other statement, and hopefully this will sink in as we go along. Okay. I'm going to make a point number 3 down here. And point number 3 is that usually only one pair of electrons on an atom. Yikes, I'm running out of room. Participate in resonance. And I'll explain it more as we get into the next few slides, but that's because in order for, right, the electrons to participate in resonance, the p orbitals have to overlap with each other. So remember, let me just underline that part, because that part's probably the most important part of that sentence. P orbitals have to overlap with each other in order to participate in resonance. So think about it like this. Let's say I'm sp hybridized. Okay? If I'm sp hybridized, how many unhybridized p orbitals are there? There's 2, right? It's these 2 here, right? So if I'm bonded, like pretend I'm looking at you and I'm sigma bonding with you with a hybridized orbital, which is kind of weird, I know. And then I would have 2 other p orbitals. One p orbital would be like this, right? And the other one's like this, it's at 90 degrees. So it makes like that X. Right? Well, or a T or a cross, because the next is that. Okay. So if we're going to be in resonance with each other, the orbitals have to line up. So let's say you have a p orbital, and we're going to have 1 pair of electrons involved in resonance. I'm bonding to you with this pair. This is at 90 degrees. It can't line up. So it can't participate in resonance because it's at 90 degrees to the one that is in resonance. Okay? So if you have these 2 p orbitals, now this is 2 different atoms, right, that are like this, and they're involved in resonance. If this has a second pair of electrons, it's usually not involved in resonance because this pair of electrons is not lining up with this one. Okay? You'll see how that's important, hopefully in a little bit. Usually 1 pi bond at a time. So if you have a triple bond in a conjugated system, it's usually just one of those that's involved in the resonance of the system. Okay, so now here's another very important idea, okay? It says, to allow for delocalization, resonance, some atoms that would normally be sp3 will become sp2 hybridized. So I usually state it like this. If a pair of electrons can participate in resonance, Golly. Yeah, I know. I got the wrong letters in there. Participate. I always got precipitate and participate in my head at the same time, and I couldn't get the word out. Okay, so if a pair of electrons can't participate in resonance, it does. And the consequence of that, that's more practical. The consequence of that is it might look like it's sp3, but it's really sp2. Because it's part of the resonance system, it has to be in an unhybridized p orbital.
Let's say if a power of electron?
A pair, yeah, sorry.
So you're saying that nitrogen is sp.
Right, look at that nitrogen. This is the point of this on this slide. That nitrogen's an amide, okay? In an amide, you have a lone pair of electrons, right? That's on the nitrogen that they drew. They didn't draw the ones on the oxygen because they don't care about those ones right now. You have a pair of electrons on the nitrogen and then 3 other groups, right? So that's 4 groups. So everything that you learned, like in Chem 1A, says that's sp3, but it's actually sp2 because it can participate in resonance. And you know that only after you draw the, well, okay, you know that because I told you, but you know that only after you draw the resonance structures by pushing the electrons. It's an allylic lone pair, right? The nitrogen will contribute electrons to this bond, and then this bond will go like that. And what you end up with is your resonance structure. And remember, R stands for the rest of the molecules. It actually stands for what's called a radical, but I don't know. I'm not into that old nomenclature. Now, what makes this possible is that the oxygen is more electronegative than the nitrogen, and so it pulls that pulls the electron from the pi system and pulls the negative charge onto itself. Okay. And now that nitrogen is sp2 because now it only has 3 groups on it, not 4. So, like I said, if a pair of electrons can participate in resonance, it will. Now, if it had 2 pairs of electrons, only one of the 2 would participate. That's why I said that thing I said before. Yeah, they have to line up.
Why the structure on the left is much more stable than the structure on the right?
Yeah.
Because the forces are all neutral and everything.
Yeah.
So why? But it does still have that shape because of resonance.
Yeah. And it is, again, in the hybrid, what the molecule actually looks like is the hybrid. It probably looks more like the amide than the resonance structure of the amide. Okay?
It's more.
Yeah. Yes. Yeah, I thought of a whole bunch of other stuff in the back of my head, and I just said, no, the best answer at that point is just yes. Okay. So, yeah, it's sp2 hybridized. That's all what this says down here. And it says why is sp2 generally less stable than sp3. That's actually one of the lines that's left from the book, and I thought, well, I'll leave it in there because I don't really know why I actually don't know why, clearly. sp2 is less stable than an sp3. I think they're talking about a specific instance of, I don't know. I'm not even going to go into it. I think, I know. Well, okay. It's not specifically because of that, but the reasoning that I think it is because when you delocalize electrons, it makes the structure more stable. But that would make sp2 more stable than sp3. So I don't know. I just left that sentence in there. You can scratch it out if you want to. Or if somebody can find the answer in the book, I might just be like so happy that you did that for me.
Maybe because carbon normally wants to make sp3 stable.
Well, carbon wants to make 4 sigma bonds, and 4 sigma bonds are more stable than a sigma, 3 sigmas and a pi. I don't know if that's the kind of stability they're talking about or not. I don't know. Doesn't matter to me that much. Okay, so this is this does look less stable. The amide resonance structure looks less stable, but one of the statements that they make, which is good to think about, delocalization must be very stabilizing if it can favor sp2 over sp3. Right.
Yeah, that is.
Right. All right. Okay, so back onto this overlapping orbitals business. When you have delocalization of electrons, like in the amide here, you have 3 p orbitals side by side that can line up, that allows for the p orbitals to overlap and allows for delocalization. So if we look at this structure, right, the question is going to be, can this pair of electrons here participate in resonance like this? So this is pyridine. It's a very common organic solvent. It's slightly basic, it turns out. But can this pair of electrons participate in a resonance like this? And why can't you just draw that? Okay. And the answer is the thing that I said before. If you already have a pair in a resonance structure, the other pair can't. But what I'm going to try to do is show you in pictures why it can't. I'm going to draw it really horribly myself first, and then I'll show you the book's picture because it kind of makes more sense. But it helps to see how the picture builds up in order to show how that pair of electrons can't be involved. So what I'm going to do is I'm going to create a little whiteboard. And I'm going to draw a pyridine in its Lewis structure in the upper left here really quick. I just put the nitrogen at the bottom. Don't know why. Pair of electrons here. Now each one of these has a hydrogen on it. That makes up the bonds. So let's go through really quickly and look at the hybridization of all these different atoms, okay? All the different carbons. And the carbons at each corner have 3 groups on them, right? Hydrogen and then 2 carbons, or nitrogen. So that's sp2, 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 sp2. And let's for now just call that sp2, okay? Because if it could participate in resonance, it would actually be sp hybridized, which would be hard because it would want to be linear, but I can't even do that, okay? So this is, let's just assume that they're all sp2 all the way around. So what I can do is I can take a side-on view. So like if you're looking at my iPad, right, and that's what we're looking at now, what I'm going to do is I'm going to take it like this, put the nitrogen down here where the button on my iPad is, and I'm going to draw it like this. Okay, so we're going to be looking it on edge on a little bit from the top. So I can draw a hexagon. And then I'll squish the angles a little bit to indicate that it's on its side. And so this is the front. And that's a drawing style I talked about before. The other side's going to the back. Okay? Now, on the end, I'm going to put the nitrogen on this end, on the right end. On the left end, I'm going to put a carbon. And the carbon is sp2 hybridized. So at each carbon, I'm not going to draw them all, but I'm going to draw the hydrogen, okay, on that one. But on each carbon, there's a hydrogen sticking out. So sp2 means it has 3 groups. It's trigonal planar, okay? So these are the 3 groups on the carbon. There's the hydrogen, there's this carbon, and then there's this carbon, all right? That's all in the plane. Where's the p orbital? They're perpendicular to the plane. Okay? The unhybridized p orbital then sticks up like this. And I could shade if I really wanted to, like like that. I'm just going to shade the one so you can see it better, and because I feel like shading it. So that is perpendicular to the plane of the molecule, right? Then the other ones are all like this. And I'll draw the bottom parts on them too. And then the pi bond is actually the overlap of all of these orbitals together. Does that help to draw it? Like see it drawn? Okay, so now, actually in like a benzene ring structure or pyridine, there's lots of electron. Think of it like an electron sandwich. And the electrons at the top and the bottom, those are the orbitals. The top orbital and the bottom orbital is like the buns of the bread. And then like the hamburger or the soy burger or whatever you guys eat out of are the carbons in the middle. But then in the real middle, there's nothing. It's like a big ring, like yeah, they faked you out. It's not a donut though because it's layered, right? I don't know what you guys are thinking now. Okay, so now here's the important part. These orbitals are involved in delocalization because they overlap, right? And here I drew carbon bonded to two other carbons and a hydrogen. Now in the nitrogen, I'm missing a lone pair. The lone pair is in one of the hybrid orbitals. So it's like this. So it's sticking out of the molecule. It can't actually participate in the resonance. Okay. What that means, though, is it can participate in other things. So when we use pyridine most often is when we need a solvent that can act as a base, and pyridine acts as a base and could pick up hydrogen ions from solution. If that pair of electrons was really involved in resonance, it wouldn't have that ability to do that. Okay, so ultimately then, going back to the drawing, you can't do this because this pair of electrons can't overlap with this the p orbital here to create the second pi bond. Okay, so this is a little deceptive. It looks like, yeah, sure, why not? And then if you can't remember that, just remember I told you only one pair can ever be involved. But this one turns out to be in an unhybridized orbital. Or in a hybridized orbital. And then this one is in the unhybridized orbital. So one pi bond at a time. There's the sort of the better book picture, right? Oh, I even drew it in the same orientation. There's the lone pair of electrons. It's in the plane of the molecule. So you have to think about that molecule being entirely flat. It's like a sandwich. The carbons make up and the nitrogen make up like the hamburger patty in the middle. Except for it has a big hole. Like there's actually a hole that goes straight through here in the middle. But this pair of electrons can't participate in resonance. All right, so that's it for that chapter. I'm actually going to go to the next chapter, which is the acid-base chapter. Oh, and I'll stop this recording.